In this video, we're going to introduce the idea or concept of the mole. When I'm talking about the word mole, I'm not talking about the animal. In chemistry, the mole is just a specific number of things, kind of like a dozen. So this is similar to the concept of a dozen. When we're talking about a dozen of something, we should know we're talking about 12 things. When we're talking about a mole of something, we're talking about a huge number of things. You know, in chemistry, we're dealing with things like molecules and atoms that are incredibly small, but we're dealing with them on our scale. So we might have 100 grams of water, and we need to know how many molecules of water that is. So scientists have come up with the concept of a mole to help us deal with large numbers like that. So with a dozen, we talk about 12. With a mole, we're talking about 602 hexillion. So that's how many things, like atoms or molecules, are in a single mole. Now in this video, we're going to talk about converting from atoms or molecules into the number of moles. After this video, we're really going to be just talking about the number of moles, but I need you to understand that within one mole, there are 602 hexillion atoms or molecules. This number is way too big to deal with, so we actually put it into scientific notation, which means I'm going to put a decimal here after the first number, and then I'm going to count the number of spaces I had to move that decimal from here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Now this is a well-established scientific constant, which means everyone knows this number, and it has a name. This is Avogadro's number, based on the person who figured out this number, and it's the number of things in one mole. Just like when we talk about a dozen or 12, we can talk about anything. We can talk about a dozen water bottles, donuts, atoms, whatever it is, it's 12. Same when we talk about the number of moles. We could be talking about donuts, water bottles, or more commonly, the things we're referring to are atoms and molecules. Just know that when we're talking about moles, we're talking about this many things. Okay, let's do some practice with these numbers. Let's start by converting from moles to atoms. How many atoms are in 3 moles of calcium? Notice that the unit for moles is mol. Try this question. Here's a hint. If you think about moles as dozens, you can calculate it the same way you would calculate how many donuts are in 3 dozen. If you know that a dozen is 12, and you've got 3 of them, then you know that there are 36 donuts. The same concept can be applied with moles. We know that the number of moles is 3, which is we indicate with a small or lowercase n. And we also know Avogadro's number, which is our 6.02 times 10 to the power of 23. Notice there's no units here because this is just a number of something. What's required is the number of atoms. When we're talking about the number of something, we talk about that in a uppercase N. And it's the number of atoms of calcium. So now we need our equation. And we're going to look over here and see that the dozen, or 12, is multiplied by the number of how many dozens there are. So I'm going to do the same thing with our moles. We're going to take a total number of atoms. It's going to be equal to the number of moles times Avogadro's number. I'm actually going to change the order of that. So this is like the dozen, or 12, multiplied by the number of moles given. Now I can apply that equation to figure out the number of atoms of calcium by putting in my Avogadro's number, multiplying it by my number of moles. And that gives me 1.8 times 10 to the power of 24 atoms. I'm just going to pause here for a second and show you what I did on my calculator to get this scientific notation. So I would put 6.02, and then to get times 10 to the power of 23, I'm going to hit this exponent button and then 23. So this exponent button is the times 10 to the power of whatever. So it's a little bit of a shortcut there on your calculator. So now I'm ready for my therefore statement. Therefore, there are 1.8 times 10 to the 24 atoms in 3 moles of calcium. In the second practice question, we're going to look at converting from moles to molecules. So remember, atoms and molecules are different. Here we have 1 molecule of water, which is actually made up of 3 different atoms. We've got 2 hydrogens and 1 oxygen. So we have 1 molecule, but 3 atoms in that molecule. So how many molecules of water are in 5 moles? So we know that Avogadro's number for how many molecules within 1 mole, and we know the total moles is 5. And what's required is the number of water molecules. What would the equation be for this question? We're trying to find out the number of water molecules, and that's going to be equal to the number of moles times our Avogadro's number. So when we apply that equation, we plug in our number of moles and our Avogadro's number. And that will give us our number of water molecules, which is 3.01 times 10 to the power of 24. Therefore, there are 3.01 times 10 to the power of 24 water molecules in 5 moles. So that's the number of molecules. What about the number of atoms? What do you think? Well, we know there are 3 atoms for every 1 molecule. And if we know the number of molecules, we would just multiply it by 3. So therefore, the number of atoms would be 3 times our number of molecules, or 9.03 times 10 to the power of 24. Now let's try converting the number of atoms or molecules into moles. So how many moles is 4.6 times 10 to the 24 atoms of magnesium? Remember, that's like asking how many dozen is 24 donuts. You can probably figure that out really easily by just dividing 24, number of donuts in total, by 12, the number in 1 dozen, and you get that it's 2 dozen donuts. The same principle can be applied with moles and atoms. So give this question a try, and then we'll go through the answer. So we have Avogadro's number, as always. And this time we know the number of atoms of magnesium. And what's required is the number of moles, which we write as a lowercase n. Just like in our donut example, for the equation, we want the number of moles, or number of dozen, to be equal to the number of atoms in total divided by however many atoms there are in 1 mole. We know that to be our Avogadro's number. Now when we apply our equation, we just sub in our numbers. Our number of moles is equal to number of atoms divided by how many atoms are in 1 mole. And that's going to give us our number of moles. Therefore, there are 4.6 times 10 to the power of 24 atoms in 7.64 moles. So to finish up, we're going to talk about a useful application of moles known as molar ratios. You're actually already familiar with molar ratios, you just might not know it. So let's take a look at the decomposition of water. Water decomposes into hydrogen gas and oxygen gas. We know we need to balance this equation. To balance this equation, we have 2 water molecules for every 2 molecules of hydrogen gas and 1 molecule of oxygen gas. We don't actually have to put the 1 there. We know if there's no number, it's just 1. Now these numbers used to balance the equation are actually the same as molar ratios. I'll show you what I mean with an example. If there are 5 moles of oxygen gas produced, how much water was there to start with? Now using the balanced equation, we can answer this question. The ratio of oxygen to water can be seen in the numbers used to balance it. There's 1 oxygen for every 2 water. Now we can use this ratio to answer this question. We know there's 5 moles of oxygen. We need to figure out how many moles of water go with that 5 moles of oxygen. So to get from 1 to 5, we have to multiply by 5. So we're going to do the same thing to the 2, which would give us 10 moles. And that makes sense when we look at our equation, because 1 is half of what 2 is. So there should be half as many moles of oxygen as there is of water. So to answer this question, there should have been 10 moles of water to start with. And the reason this is so useful will become more obvious in the next video, but just remember, when in doubt, use these ratios and figure out how many moles there are of the substance, and that's pretty much the first step of any of the questions we're going to be doing later in this unit. So let's extend this question a little bit. How many moles of hydrogen gas would there be? What do you think? Well, we know there's 5 moles of oxygen gas, and we know that there's, for every 1 mole of oxygen, there are 2 moles of hydrogen, just like there was with water. So there would be 10 moles of hydrogen gas as well. Twice as many moles of hydrogen as there are of oxygen. What about this? How many molecules of hydrogen gas would there be? So we'd multiply our number of moles by Avogadro's number, and we would get 6.02 times 10 to the power of 24 molecules of hydrogen gas. Okay, last question. How many hydrogen atoms are in the 10 moles of hydrogen gas? If we know there's this many molecules, how many atoms are there? So there are 2 atoms of hydrogen for every 1 molecule of hydrogen gas. So we would have to double this number of molecules to get 1.2 times 10 to the power of 24 atoms. In our next class, we're going to do some review and some more practice of these type of problems to get you ready to apply your knowledge of moles into more real-life chemistry problems.